So just as promised, today there's no extra lecture. It's just basically like office hours. So if you have any questions or you want, these are all the lecture slides. So if you want to go over any of them again or any part of them again, we can also do that, or go through any of the practice questions, or yeah, whatever you like. Oh, office hours. There will be TA office hours as usual, Monday through Wednesday this week, but not Thursday or Friday. Um, yeah, let me. Um, this one, 24. Okay. Oops. Okay. Design a parallel algorithm for solving the system of linear equations given by ax equals to b. Yeah, where you're given the n by n matrix A, n by 1 vector B, and compute n by 1 vector X. Yeah, so what do you think? Yes. How do you address this issue that like normally we're doing like ax equals, sorry, normally normally we're doing like ax equals to y, and you have x and a, but this time you need to solve x, and now this time you get, it's called b, but it needs to become y.
But each element X would be used twice, right? So can we create like a system of equating using this equation somehow? And
Yes. Oh, just to be clear, I don't actually have the answers to any of these final answers, so we're working that out. Yeah, so like, so for example, for B0, that's equal to B0 times X0 plus C1 times X1, like this way. And then for B1, it's like B1, C2, X1, X2. But so every X has two equations out of diffusion.
I was thinking, I look at the bottom row, it only has one unknown A in that row. So when you do those equations, you get x minus 1, n minus 1, n minus 1, you can solve x n minus 1 in that way. And then that lets you solve from, since you have the unknowns already, you can solve the x. So now we can kind of get thinking we have these prefix. Words out there.
Yeah, I think it's true. Yes, so just to repeat, the last one, only, you can directly solve xn minus one because it's dn minus one times xn minus one equals to bn minus one. And then, so you would just get xn minus one by doing like bn minus one divided by dn minus one. And then from there, you can plug it into the previous equation, which has xn minus two and xn minus one, but now you have xn minus one. So you plug that in, and now you can solve xn minus two. And the same for the, like, going back up. Any questions? You can do. So, like, it looks like xn minus one, well, you can solve x, and you have xn minus one basically up front, because you just divide b over d. And then it looks like xn minus two, like, you have an equation that depends on xn minus one. But then you have that initially, so you can and then it looks like xn minus three is dependent on xn minus two and xn minus one. But then you can like solve those through prefix all the way back up. Yes.
How much do we have to say what's the problem? Just say it's out.
For prefix sum, you just have to define what is the input and what is the operator. And like you have an output that you want, like your array of x, and then you get into the input and you set the operator, and then you can usually just expect one sentence to show that the input combined with the operator will give you the output, which is done right.
I understand that it's just like from my experience, if I write that thing down, it will give me a zero. So now it's like write the structure of the result, so I can get it.
Could you say it again?
So can you write like the structure of the end result?
Oh, like what would I write?
Yeah.
Yeah, so like for prefix sum, you have an input. Usually you have some starting condition like x sub 0, or in this case, x sub n minus 1. And then you say, how am I going to get x n minus 1, which is just divide d by d. And then you can say, how does each of the following numbers, like x sub I, depend on the previous the previous two x, or I guess in this case they're going up, but like here, for example, xn minus 2, once you have figured out xn minus 2, or sorry, once you figure out xn minus 1, you can figure out xn minus 2. And then if you want to figure out xn minus 3, it depends. Once you have xn minus 2, that's enough to figure out xn minus 3. But you need to solve that, you need xn minus 1. So then from there, you would say like how does each output correspond to how you ran prefix on that input.
So basically, first we will take input, and then we will get we need to explain how we get the xn minus 1.
Mhm.
And then we use the back substitution using the prefix sum.
Mhm.
So is that like a good answer for TA?
You need to be clear about the operator and the inputs.
Okay.
So like with prefix sum, you can do any arbitrary binary associative operator. But here it's not just like as easy as multiply or add or something. Like you need to plug it into the equation. And then with each equation, you can get an expression for x sub I, but you need to get that expression.
So in this case, with your operation, x of I is divide minus x plus 1.
Yes, please. This one? Design parallel algorithms for multiplying two and by matrices using NQ processors. So EREW is exclusive read, exclusive write, and CRCW is concurrent read, concurrent write in the sum model. The first one is to run in log, and the second one runs in order one. Ideas?
You have NQ processors, so I don't know, for your EW, you just have every processor like load the pair of IUK and KJ that it needs, multiply them and then do like stuff like I don't know if parallel prefixes are the right, I mean, like you could implement it in the shared memory. That's sort of what you would do, right? You could just like write to this cell and then write to the next cell. And then the sum is the login.
Exactly, yeah. So because they have NQ processors and there's NQ operations that you need to do, because the operators have n squared, and each entry has n multiplied going into it. So every processor does one of the multiply additions, and now you need to aggregate them somehow. And so you aggregate them in EREW because you can only exclusively write to one cell with one processor at a time. You can use like the tree that we have been doing for reduce. And then in CRCW, in the sum model, anybody, like arbitrarily many processors can write to the same cell in order one time. They can sum up numbers in order one time, arbitrarily to one sum. So that's why it goes down to order one. Yeah, so you could say, so you have NP processors, each one of them does one multiply, like some pair of the A and B matrix entries, and then I need to add them up. Like Cij is the sum over K of AIK times BKJ. So now to do that sum so it takes order one time in parallel for everybody to do one multiplication, and then to aggregate them takes log n in EREW. Yeah, no, that's totally fine. Like to get log n, you would just, you could just say like, then you would do like a tree like reduction with log n levels.
You have n squared processors so that you can, like, sorry, n squared grid. Right? There's one set of processors. So, yeah.
Yes, exactly. So all n squared reduction, there are n squared reductions, and each one has length n. So all the reductions happen in parallel, and the log n is the length of any single reduction in parallel.
From EREW DRAM to like the normal.
Okay, good one. The difference between PRAM and binary forking is that in PRAM, so in both of them, you basically simulate infinitely many processors, and in PRAM, a parallel for loop with n iterations takes order one time, takes order one parallel time, and in binary forking, that would take log n time. And that's pretty much the only difference. And then there are these variants of PRAM that basically depend on how much power you have to write or read in parallel.
So if you have like parallel for loop, they all just do that.
Yes. I guess binary forking, they haven't really defined so many variants like this, but it's basically concurrent CREW. You can currently read from any slot as many as you want, but like a sum over n numbers in binary form takes log n time. One, because the parallel for loop takes log n time, and also because you cannot arbitrarily write to the same slot in parallel. So you have to do the true left reduction for log n. It's gonna be like the structure of the previous exams, like different section. Every question has like several sections in it. Yeah, the content is the same with a couple extra topics, but yeah, everybody just writes their exams differently. And so, we can see in the previous couple of exams, it's the same format that we will have. So the question was about building quantities in parallel. Yes. So how would you build the quantity sequentially? Step by step. So you start with if you started somehow. So assuming that you have some set of points and assuming that they're not sorted, first you sort them and then you can divide them into 4 quadrants based on the spatial area. And now you have 4 subproblems. And then you repeat the process in each one of those subquadrants until some stopping condition. Usually you can either fix the height or you can fix the minimum number of points in any box. So if it's that way, then some paths in the tree may be longer than others because they may be more clumped together. So which part of that can we parallelize? Well, we can parallelize the sorting part. Depending on, so there's basically 2 steps at every level. One step is potentially sorting if you need to do it again. And the second step is determining where everybody goes in the different quadrants. And so the sorting can happen in parallel with any sorting algorithm that we have done, like Pythonic sort or something. And the partitioning can happen in parallel too, because you have endpoints and you know what the quadrants are, they're just spatial coordinates. And so in parallel, you can evaluate the quadrant 2.1 and quadrant 3.4. And so you do that step, everybody can figure that out. And now you need to tell, you can either repartition, you can shuffle the array again to put like quadrant 1 all in the first and then quadrant 2 and quadrant 3 and so on. And that you have to figure out how big each quadrant is, which you can also figure out in parallel because you just sum up. You basically have sort of like a flag that tells you which quadrant you're in, and then you can sum up how many flags have 1 or 2 or 3 or 4. You might not need to sort. So you could do this, you could just keep the sort. You can do, so this step, you just figure out how many particles are in each quadrant. And that sorting makes it easier, but that you could do without sorting, because all you basically need is all the particles in quadrant one in the front, and then after that, all the in quadrant two, then after that, all the particles in quadrant 3 and 4. And so you, without in parallel, you just figure out how many are in quadrant 1, how many are in quadrant 2, how many in quadrant 3, how many in quadrant 4. And then that kind of like we have to do with prefix, that tells you the starting point of each of the quadrants in the array. So you sort of like a quadrant partition, you put all the ones in quadrant 1 first, and you put all the ones in quadrant 2, quadrant 3, and quadrant 4, and then you can just reverse. You don't need to sort technically, but it is nicer to sort because, like in the homework, when you have it sorted in important order, you don't need to actually do any shuffling. You can just do a search to find the correct end of the partition, and then recursively just find end of the partitions. Did I answer the question? Yes.
Lecture. So, could you please go back to the example of adaptive or tree? Slide. So for this one, you said it's from the southwest corner and then go counterclockwise. But then there's another slide which is slide 18. So this step is from the top left and go clockwise.
Oh, I see.
So which one we should use in this step?
Anyone is fine, as long as you know which one is which. You can say like which direction you're going in, or if there's a question like this, I will say like just go in this direction. Yeah, it does, like when you think about programming this thing, say you're actually like think about if you're going to write this code, you would have one node per node, and then each one of them would have like 4 pointers. It would be like pointer, like node pointer northeast, node pointer southeast, node pointer southwest, node pointer northwest. So like this layout is just for illustration. When you actually write the pointers, like they're just wherever in memory. So yes. So maybe we can go here first. So this is like the tree that we need to recursively evaluate in the parallelization. And you can think of it as we start with the whole polynomial, with 0 up to 7 coefficients. And then now we have 2 halves, the even and the odd half, and P0 and P1. And those can be evaluated in parallel because they don't depend on each other. And then you recurse again, and P0 gives rise to its own even and odd. And then P0, 0. P0, 0 is like even, and then P0, is like even odd. And then you keep going down from there. And so there's only 8. So the last level is, you can represent them as bit streams. Where 1 means that you are odd at that level, and 0 means that you are even at that level. And you can evaluate all the leaves in parallel, and then going up the tree. So this is the illustration. Actually, technically it starts on the left side. So the inputs are omega 0. And this is like level 3 in the tree. And then it's like 0, 4, 2, 6, because those are the combinations that come together to make the polynomial at level 2. And there's a few more. So the number of levels that we have is b, which is log. And u is if you reverse the rank of your, so you have a rank, which is a bit string, and you're going to reverse this bit string to get which coefficient you're computing. And what u tells you is basically who is your rank and whether or not you're going to, and your rank tells you whether or not you're going to send or receive. This last if bit, like if the ith bit of your rank is 0, then you have u, and it's basically telling you whether you're the left or the right child. And if the ith bit is 0, that means you're the left child. So then you're just adding to yourself. Otherwise, you're adding what came from the right child. Oh, reversing the bit string just is like flipping it. Like if it was 0, 0, 1, for example, reverse is 1, 0, 0. Okay. Oh, why does it help you get the coefficient? Because if you look at this, so it's like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. And 4 is 0, 0, 1 flipped. And 2, well, 2 is just 0, 1, 0, so it's the same if you reverse it. And 6 is 0, 1, 1 flipped, because 6 is 1, 1, 0. So the ranks are going 0 up to 7, and the coefficient that each rank is computing is the reverse of its own bit string. In the exam, you will not have to know like the details of the parallelization. Actually, I think in the formula sheet, the time is given, like n log n, and the questions will be similar to more like in the homework, like how you use it to compute something. But one level deeper. And sorry, there's a question I'm going over like the related homework question. This one? Sorry, let me open the actual question again. The question is, you have two vectors, A and B, and then convolution is defined like this, C, where C is the sum. Let me figure. This expression, so sum of numbers, J goes up to I, B sub J, and then the second part is the second half of I plus 1 to n minus 1. So the first half is like J up to I for some I. Then the second half is J starting from I plus 1 up to the end. And the second half is still A sub J times, but now B is coming from the right. As J goes up, the subscript of B is going down, and whereas like on the, well actually on the right side, on the left side too, A is going up with J and B is going down with J. But the thing on the right hand side is like starting from n, well, starting from n plus I, the thing on the left side is starting from I. Okay. And you want to compute this positive route convolution. And it's both two processors. So what do you get if you just run the FFT on A and B? Which coefficients do you get? Well, if we look at this line, you get this thing, which is like the coefficients of everything on the bottom, which is on the actual right side, like the thing that we want to compute on the left, which is like a sub j times b sub I minus j. So we would get that all on the left half when we compute 50. And then the thing on the right was this, but it was like the n plus I minus j. And so, but those are still within the range. Because j is at least I plus 1. So b plus n, or sorry, b n plus I minus j is at most n. So it's still like, and it's still the second half of what we're computing. And so that's why the answer is like this. Oops. So you get, if you have 2n, if you have 2n degree polynomials, or 2n minus 1 degree polynomials, the output polynomial has degree at most 2n minus 2. So you're going to get 2n minus 2 coefficients in the output. And you want n coefficients in the end, because, or you want n numbers in the end, because you're combining them to compute the convolution. And those two terms are just combining the ones on the left half and the ones on the right half. And the partner is halfway across. So for all I, the partner is n plus I. Yes, you can go to some matrix caching. How far back should we go? Or is starting here okay? Do you want to start with the caching models? This one. So, is everybody caching models? Maybe I can very briefly recap caching models. So, in the caching analysis, you have two parameters of m and b, where m is the size of your memory in bytes, and b is the cache line in bytes. So the number of cache lines you have in your memory is m over b. And it takes order 1 time in this model to bring b bytes of stuff. So ideally, we would like to get factors of m and b in your runtimes. Because, so for example, if you read just one contiguous array of size n, that takes n over b cache misses, order n over b cache misses. Because like there might be stuff at the end, so it's actually like rounded above by n over b plus 2, because you might have stuff that like exceeds on the end, but the main part is n over b. So this cache miss lemma is saying, if you have R data segments, R contiguous data segments, and each one has size s of 1 bytes. And suppose that if you add them all up, it is equal to n bytes, which is at most m over 3. And n over r which is the average size of each, segment, n over r is at least b, which is the block size. Then this is saying that all the segments will fit into the cache, and the number just to read them is m equals 3n over b. So this is theta n over b. Actually, it doesn't matter. So the second part, as long as they're all contiguous, it doesn't actually matter if they fit in the cache or not, because like to stream an arbitrary large array of size n, it will take you n over b cache misses. But the first part depends on how big the segments are, which is that they're going to fit. The first part of the Copeland lemma is that they're going to fit into the cache. And they're going to fit in because all the segments, there are most m over 3. And so the number of cache lines that they will require is at most something like order m over b, because they're all contiguous. And the m over 3 is just kind of like to be safe, because if you have extra parts on the left and the right side, then you're gonna have to create one more cache miss. Like it'll take you one whole cache miss to read this part, even though it's less than one cache line. And same here, like it'll take you one more cache miss just to read this tiny part. It just happens to go once. I would say the actual like constants of like 3 are not super important, but the main point is that in this case, the segments can all fit into the cache, and also the second part is that it takes n over b cache misses to read n contiguous bytes. Oh yes. Yeah, so related to the cache lemma, the cache lemma is a very high-level thing. It's like you have these segments and they all have the size. The lemma is general enough that they can all be different sizes, but actually, you can do a matrix as a sequence of these segments, where each row is however many elements you have. And so, like if you call that n, so like if the matrix is n squared size, and every row has n elements, then it takes n over b cache misses to read one row of your matrix. And the point of the submatrix, or the point of the caching lemma, and later on will be used in submatrices, is at what point does your submatrix start to fit in the cache? Because once you have submatrices, they're no longer, like if it's a row major, the whole thing is contiguous. But if you take submatrices, that's just kind of like the way you use like a bunch of sections in your long array. And yeah, so in this caching model, we assume that we have at least polynomials. The cache size is at least b squared. So the cache size is at least polynomial in the line size. And the reason for that is because you need, if your matrix is BIB, you would like it to fit in the cache. Like if you have one line, like you would have at least 3 lines. That's like a reasonable assumption because cache is there. So that's the issue. So you can just assume that it has a size at least b squared. And then, so going directly from this question that we just talked about, you can view each row in your submatrix as a small n by small n. Well, it just has small n elements, this example. And suppose that the size of n squared, which is the submatrix, is at most m over 3, which is the thing that we had in the caching lemma. Then the number of misses, then the submatrix will fit into the cache, and the number of misses you take to read them all is theta n squared over b. And that just follows from plugging in the numbers related to the submatrix into the cache lemma. So the main part of this is that when we use this in matrix multiplication, we want to cut the submatrices. So we cut the matrix into submatrix multiplications, and we want to cut them such that the submatrix fits into the cache. And the way you do that is to cut them so that they fit these parameters. And the reason that you want to cut them so that they fit in the cache is because then you can get factors of m and b in the denominator, Or you can always get factors of B, pretty much. That's the trick. You can usually get factors of B more easily than factors of M, but you can get factors of M in matrix multiplication because the work is polynomially larger than the size of the input. And the way that you do that is by reusing the matrix that is already in the cache. So at the beginning, it's not like it's in the cache, but you put the submatrices, you multiply them in the cache, and then in the next step, you reuse one of the submatrices that is already there. Like, for example, you have submatrices of A and B, and you compute some answer of C, but you can reuse part of A to compute another part. Answer the question? Question 4. Yeah, so it depends on the definition of question 1 through 3, which is this tableau. And to remember, tableau is, it's basically like dynamic programming. So for AIJ, it depends on some combination of the up left neighbor, which is I minus j minus 1, the left neighbor, which is I j minus 1, and the up neighbor, which is n minus 1j. If you imagine like it's a 2D grid. And so this is how you compute like edit distance, for example. So the simplest way to compute this is through double formulas. I up to n, j up to n, and you just plot the 2D table. The part was about 4.3. So, does anybody want to contribute to people are really it's kind of like a lot of you. So just yes, yeah. So we start with the recurrent solution. So there are two cases. Usually when we do cache analysis, there's two cases, which is when the problem does not fit in the cache and when the problem does fit in the cache. So we can start from the base case. For form construction, there are 4 subproblems. So like Q of n equals 4 times Q of something. And what is that something? Well, here n is the, and remember we were doing this trick that like you only need n space to compute this thing because you can do like switching the rows. So the size of the problem is n. Or sorry, the size of the input is n. The total computation that we're going to do is n squared. So how much does n decrease in every one of the subproblems? Four. Is that number 2? Because, yeah, it's a good point. So there are 4 subproblems, but each N is just the side length. So if you cut both side lengths by 2, then you cut the whole grid by 4. Okay? So it's Q of N equals 4 times Q of N over 2 plus something.
So in this case, that something is constant was give an example of when that something is not constant.
Yeah, so like a word sort, for example, T of N is 2 T of N 2 plus theta N, because the merge step takes theta N. Or if it's sorry, the partition step takes theta N.
So is that something you the sets
Yes, exactly. Yeah, good point. So when you have a recurrence relation, you have the recursive part, which is like number of subproblems times Q of how you cut the subproblem, plus the work that it takes you to combine the subproblems together. And in this case, small, but there are other cases where it can be linear or even possibly greater than linear. So if you remember matrix multiplication, we had 2 formulations, one where the plus f of n was theta 1, and one where the plus f of n was theta n squared. N squared. But that plus and theta can be however large or anything. And if you remember like the Master theorem, tells you how to relate the size of the subproblems and the number of subproblems with the f of n indications are just how they correspond to each other. So that is part 1. And then if you draw the recursion tree, then the recursion tree comes from like the branching factor is how many subproblems we got. And each one of them has size n over 2. So the height of the actual computation tree is log. Because you start with n and you cut it in half every time. Okay. So that is the height of the actual computation recursion tree, log. But this part is about cache complexity. So we missed the second part of the recurrence, which is you need a base case. And the base case is when the problem starts to fit in the cache. And here the input size, the data size is proportional to n. And so the base case is when n is similar to the cache size. And it takes n, or like, yeah, so when n is similar to m, then you don't need to keep recurring, and the cache misses that it takes is proportional to m over b. So yeah, so when you do cache analysis, there's 2 cases. One is the part where you keep recurring, and the second part is when you have fit in the cache. And to be clear, the algorithm keeps going once you start fitting the cache, but this is for analysis purposes. It's like once you fit in the cache, you no longer need to incur any misses, because the part that you have already is the part that you're still computing on. But if you actually write the recursive algorithm, like you recurse to some base case where n is like theta 1. So the way that these cache analyses work is that you take the height of the tree of, if you weren't doing cache analysis, so just log n, and you basically cut off the bottom part after you have reached the point where you start fitting the cache. So the height of the tree of the actual computation part is log n. And you know that the base case happens when n is theta m. So what is the height of the tree after you start to fit in the cache? Yes. Yes. So the remainder height is basically log base 2 of m. Maybe m over b. So it's similar to m. I can check the exact solution later, but no, I think it is when n, no, it's when n is similar to m, but then the cache miss is incurred in that case is m over b. So the height after you start to fit in cache is log m. So the height before is log n minus log m. And so how do you get the number of leaves to the recursion tree? You have the fan out and you have the height before the caching recurrence analysis ends. And so you do fan out raised to that height, which is 4, which is the fan out raised to log n minus log m. Okay, the solution again too. So 4.2, the height is log n minus log cm, which is order log m, is used as the constant, because like by log rules, subtraction is division inside. And so if you raise 4 raised to LG is log base 2, then you get n squared divided by c squared, which is just a constant, over m squared, because 4 is 2 squared, and then by log rules. Does the 4.3 make sense? Yeah, and then to get 4.4, the question was derive the simplified assumption, well, or derive the simplified form. To get to the last step, you have the number of leaves. You have the cache misses per leaf, which is m over b, beta m over b, and you just multiply the number of leaves by the cache misses per leaf to get the total cache misses. We will not be considering such problems.
Why does it count the square of the height, or the square of 2 to the height, or 2 to the height, or 4 to the height?
Oh, so the number of leaves is fan out times, or fan out raised to the height.
Oh, wait, right.
And so fan out was 4. Slide 31. 34, sorry. This. Like this one? Yes. Yeah, so this is just the 3D version of matrix multiply, and it's analyzing the cache misses for the whole thing, just based on the difference, just based on the relationship between the matrix size and the cache parameters. So the first case, so you have n by n matrices, and we're just considering what happens when just the axis to matrix B, because the axis to matrix B is like a lower bound of how many cache misses we have to incur overall. So if n, which is precisely, is greater than some constant m over times m over b, then assuming LRE, so A is stored horizontally, both A and B are stored in a row major, and B is being accessed column-wise. So every time so we start here, and we're going this way. So we read this element, and then now we have to read this element because we're like the first element of A times this one, second element of A times this one. So each of those is one cache miss because they're not in the same block. And the problem, like once you get to the end of here, Now we're gonna go up here, and let's say we're just in the same row of A again. This block has been evicted because n is greater than m over b. We only have space for something like m over b blocks anyway, because the total cache size is m bytes. So this is more than m over b blocks here. So by the time you get here, this one is done, and now you have to bring it back in. So that's why, so every read in B will incur one cache miss. And you have to read B n cubed times. So that's where this case one comes from. And then in case two, n is somewhere between root m and cm over b. So one column of blocks can fit in the cache. But the whole matrix does not fit in the cache because n squared is more than m. And so we do the similar argument. So we're going to read this and then this way. But now, because we're in this case, this block is still in the cache by the time we got here. So we get a factor of b in the reads too. We get a factor of b in the reads to the matrix because you don't have to incur another cache miss to read this one, or any of them down the second column. But eventually, you're going to read more than b columns, and so we're going to have to incur some more cache misses there. And so that's why it takes n squared over b to make one pass over this b matrix, and you have to make n passes. So the total, this is in this case, the b is n cubed over b. And the last case is just if the matrix fits into the dash. So this is n is less than root m, so n squared is less than m, and you only have to make. So you're still doing n cubed work because you always have to do like every entry you see takes n multiplications to go into it, but the cache miss is only proportional to n squared over b because once you bring this in, it's already in the cache and it can fit. So it doesn't need to. You don't need to incur any more cache misses to come back around. So the actual question was on 34. And so this is about tiling. So tiling is, right, so normally in the simplest version, you have just 3 loops. Each one goes 0 up to n. But here we have 6 loops where instead of going all the way down, you cut submatrices to multiply. And the submatrix is S. And so the size of the submatrix is S squared. And so the work is how many iterations are there out here? Well, you go 0 up to n, but you go up by s. So it's n over, each one of these is n over s iterations. Because it's like, 1 up to n, but plus s every time. And then the inside 3 loops, each one has length s. It's like I equals I1 up to I equals I1 plus s. So each length of this one is at most s, and there are 3 of them. So it's, these 3 have volume s cubed. And how many times do you go around these 3? It's n over s quantity cubed. And so that's what this is. And so the total work is still n cubed, which is expected because we haven't done any fancy tricks to reduce the actual number of multiplications in the matrix multiply. It's just cutting them up in a different way. And the reason that you would be interested in cutting that up into tiles is because each of these tiles can fit. If you cut them up right, each of the tiles can fit into the cache. And so you would get them into case 3 previously, which is you don't need to do additional cache misses to multiply with those matrices again. Okay, let's go back.
still have like 4 blocks that need to process.
I see. I think there's two questions. So the question is like, in the lecture, this is two-way or four-way, I guess, subproblems, two-way splitting along the dimension. In the lecture, we could split it more ways. Like if you cut it n/3 rather than n/2, you get 9 subproblems. And the reason we were interested in doing that in the lecture was for span, like you can improve the span if you cut more ways. Like you kind of can imagine it like in a wavefront way. Like first you start on the left, and then you're like this, kind of you're going like in these diagonals, and basically you're cutting more diagonals when you cut more subproblems. So one tricky part, I guess, is that we don't have great compositions of work, or we don't have great composition of spans and cache misses, actually. We have like worst case bounds, but they're not very tight, and so that's one issue. In terms of cache misses alone, if you made this 9q n/3, the height would be log base 3 of this thing, and the fan out would be 9. And so the cache, this number of leads would turn out to be the same. Yes, with sometimes, but we will consider them separately. So in this case, it doesn't help you for cache misses to cut it more ways because like this thing goes up. This thing would become 9, this thing would become n/3. And so it'll be like 9 raised to log base 3 or something, which is maybe the same thing. Yeah, so we will not be considering them together because actually it is better. One question? Consider the following embedding of a P by P 2D mesh into a P squared processor array. Processor ij is P times I plus J in the array. So you have a 1D array, like your actual, so the source, yeah, so you're trying to embed the source into the target. The source is the mesh, and the target is the array, which is a 1D thing. So what is the dilation and the congestion? Well, what are the neighbors in the P by P mesh? So the neighbors are like up, down, left, right. And the neighbors in the array are just left and right. And so dilation is like how much does the path increase after you do the embedding. So how long would it take you to go from, so like the left and the right neighbors are the same, but the column neighbors become challenging. Yes, so I think the term of the dilation is P because you said like normally for columns in the mesh you have to go 1, but in the array you have to go P. The congestion. So there's no additional, I think the row wise is fine because congestion is, so congestion is like normally if all your, so normally there would be no congestion in the initial source embedding because like it's just, you consider everything separately. But in the target embedding, multiple source links may target, or one source link may become a path in the target embedding. So now like some of them may overlap. So what is the target congestion? Well, normally with the column wise, there's no issue with the congestion, but now consider two column wise steps where, yeah, so like one column becomes, one step column wise becomes P for the step down. And that, so like one, and then what about the column wise step to the right of that? Oh, so from there, so there, with just those two steps, like the two column wise steps, the congestion, if you just consider this, is two, because now like the same, what previously in the source had no overlap, now has two processors trying to use the same link. But now you need to repeat it P times, because they're P like similarly column wise steps. And so I think the congestion might also be like P. Actually, is it more than that? Because the horizontal steps also need to use those. The one column step at the beginning of the row overlaps all the row wise steps in that row. And so maybe it's like two. And then what is the question?
That links to each other, right?
In the array.
Oh, it's a linear array, so like.
So in the array, you only have left and right.
They only have, okay.
And so, like each column link in the source corresponds to P horizontal effects in the array.
Right.
Oh, I see. So you're saying like rather than 2P, it's like P plus 1. Yeah. Yes, because the way that the column links work, there's P of them in one row. And so those overlay like P times out of relink. And then, yeah, you get one more. If the row wise, it's just like, just one string.
About the experiencing for one and questions I'm just confused on the way the name consists on that.
You have two parallel algorithms for solving a problem size n. you need some X copies of the problem, and you have P processors. I think this is asking like, so for some settings of processors, you're going to get less. So like, it looks like so the first one, the work is n squared times root n. And the second one, the work is n. And so there's some settings of processors where the first one is not efficient. And so the question is like determine the settings of the number of processors and the copies to reach the work efficient problem, or to reach the work efficient value. If I end up with something like this, it will be, I think more direct, it will be like to reach some runtime, like which settings of energy give you this runtime or something.
For as long as X is less than some like some inequality using the three variables, like the first one would be better, otherwise, is that how we?
Yeah, you could be like, yeah, for if X is some like, yeah, algorithm one is better when X is something, otherwise algorithm two is better. For different settings of P, algorithm one is better, otherwise algorithm two is better.
Like answer it in different parts of each of them, or we consider X and P together? Right?
I think I do like 3 separate parts. Oh yeah, we have 2 more minutes. Anyone have any questions? Yeah, so there's different. So when you double like the values and you try to reason about like, the relationship between N and P, it's like called fixed point scalability. And for this one, I think it's just general scalability, which is on how many processors, like earlier. Earlier in the slides, we had something like this, which is independent from the actual settings of N and P. It's just like comparing the speed of efficiency. And then from there, well, there's difference lemma. But from there, we had something like this, which is that you can compute the work for the specific product. So this was before the commit became anything, which is like trying studies of N and P, like doubling them to see the relationship between N and P. It's just like with actual expressions. In order to calculate speed up, do you need the zero? Yeah. Here, I think we just maybe somewhere earlier. Yeah, so here the speed of the serial work is NQ, or the serial time is NQ. The question is not about speed up, it's about minimizing the runtime. So yeah, it's true that you cannot calculate the speed up without the serial runtime. But here it's just giving these two algorithms which will minimize the runtime between the two under some parameter settings. It's not necessarily that it achieves the best speed up or it's the most efficient or
If we have two algorithms and they have like exactly same speed up and efficiency, but one of the algorithm uses like more number of processors, so we would prefer that one.
yeah, if you have the same speed up and efficiency, you would pick the one that can use more processors.
It's like one final thing, it's like, what about the segmented prefix scans? How, we have to worry about those, or they like, how would you solve this sort of problem with them?
You can just use them as a, like, you don't have to prove anything about the runtime. You can just use them if necessary. They have the same runtime as the regular prefix.
Yeah, alright.
Anyway, see you Friday. Unfortunately, I'll see you at 8 AM, but it's okay, we'll all be here. Oh, I think, I forgot if I said this, but the TA office hours will be Monday, Wednesday,